I deployed a smart contract to every ZK-EVM, including Polygon, Linea, Scroll, Taiko, zkSync, and one more chain that you might not have heard of that we'll talk about at the end of the video. In this video, I'll show you how all of the ZK-EVMs compare based on everything I learned throughout this process, and we'll put all of the ZK-EVMs in the market into a scale that kind of compares these different ZK-EVMs implementations as defined by Vitalik. Let's get right into it. The first thing we need to understand is how your smart contracts end up in the Ethereum virtual machine, better known as the EVM, and is what all of the ZK-EVMs that we're going to explore are trying to kind of replicate and inherit the properties of. As a dev, you're typically writing in what's called a high-level language, such as Solidity, to write your smart contracts. The thing is, the EVM can't understand Solidity or any other high-level language. It needs to read bytecode. So we need a way of converting our Solidity into bytecode. And the way that this happens is through compilation. So your Solidity code gets taken, it gets transformed into what's called opcodes, and those opcodes get transformed into bytecode that the EVM can understand. Opcodes are essentially everything that the EVM can perform. So very basic things like storing things in memory and reading things like memory are opcodes that the EVM defines. The reason any of this matters is because some of the opcodes that the EVM defines are more ZK unfriendly than some of the other opcodes. This leads us to the main challenge of creating an EVM compatible zero knowledge rollup, which is that the EVM and Ethereum as a whole were not designed to be friendly for ZK proofs, and a lot of the aspects of the EVM and Ethereum are very difficult and computationally heavy to generate zero knowledge proofs for. So this leads us to where we are today, where we have a couple of different teams building ZK-EVMs, but each team is approaching it in a slightly different way in terms of how equivalent it is to Ethereum as a whole or to the EVM in terms of how those opcodes behave. For example, some have opted for full equivalency to Ethereum or full equivalency to every EVM opcode, whereas some have kind of gone the other direction and said, hey, what if we change some aspects of Ethereum to enable new use cases? In the middle of 2022, Vitalik, the creator of Ethereum, came out with this blog post defining 4.5 kind of broad different categories for which ZK-EVMs can fit into. These 4.5 different types of ZK-EVMs fit on a scale or a chart that live somewhere between fully optimized for scalability, which is kind of how quickly and how resource efficient you are in generating zero knowledge proofs to prove batches of transactions that occurred in your ZK-EVM. And the other end of that scale is how equivalent you are to Ethereum. So the more equivalent you are to Ethereum, the harder and the more time consuming it is generally to produce and prove batches of transactions using zero knowledge proofs. So on this side of the scale, where we're fully Ethereum equivalent, we have what's called a type 1 ZK-EVM, which is fully Ethereum equivalent, meaning they don't change any part of the Ethereum system to make it easier or more optimized to generate zero knowledge proofs. Next, we have type 2, which is fully EVM equivalent, meaning it changes some internal representations like the storage of the state of the chain for the purpose of improving zero knowledge proof generation time. So essentially, it's not exactly the same as Ethereum internally, but from an application or a smart contract developer perspective, everything looks and feels and behaves the same. Next, he defines type 2.5, which again is fully EVM equivalent, except for the fact that it increases some gas costs for some operations to significantly improve the worst case scenarios of prover times. Next, we have type 3, which is almost EVM equivalent, meaning it makes some sacrifices in the exact equivalence to the EVM, meaning maybe some opcodes behave differently or some opcodes might not be supported yet to further enhance the prover generation time. So this includes some changes to the EVM that do touch the application layer and the smart contract developers might need to have in the back of their mind and consider when actually building on these chains. For most devs, this is very edge cases that this is actually going to affect, but you might want to be aware of these potential differences to the EVM when you're a smart contract developer on these type 3 EVM. The thing about type 3 is no one actually wants to be type 3, right? No one wants to have these small differences from the way that the EVM behaves. Typically, as we'll see throughout this video, the companies, the ZK-EVMs that have the type 3 ZK-EVMs are slowly kind of chipping away at the final differences required to actually transition into a type 2 where they're fully EVM equivalent. As we mentioned before, the EVM and Ethereum are not specifically designed to be ZK friendly, so some final opcodes or precompiled smart contracts to match up with the EVM might be more difficult than others to reach that full type 2 ZK-EVM where you're fully EVM equivalent. Finally, we have type 4 ZK-EVMs, which are high-level language equivalent ZK-EVMs, which means they compile your smart contracts written in things like Solidity to a zkSync friendly language and actually prove that, which means it results in much faster proof of times, but introduces a whole nother layer of differences in the development environment that require some kind of special knowledge for you to actually write smart contracts for this type 4 ZK-EVM. It actually produces completely different bytecode from all of the other types of ZK-EVMs that we've seen so far. And we'll look at what that development process looks like later on in the video when we reach the type 4 section. Okay, so now that we understand the different types of ZK-EVMs and how they fit in terms of proof generation time and Ethereum equivalence, let's start at this side of the scale where we're matching Ethereum exactly. We're going to start at type 1 ZK-EVMs. And currently on the market, Taiko is aiming towards a type 1 ZK-EVM, which is a ZK-EVM chain currently in the testnet phase. The benefit to being a type 1 ZK-EVM or aiming to be a type 1 ZK-EVM such as Taiko is that you get all of the same development experience for writing smart contracts in the Ethereum world. You get all of the benefits of software such as the node client software to actually run a node and participate in the network is usually identical, if not some very minor changes to what Ethereum does. And you essentially get all of the great aspects of Ethereum and bring them across. The main downside to this is, as we kind of mentioned earlier, it is very difficult to generate zero knowledge proofs for some of the aspects of the Ethereum ecosystem, as it's not designed to be optimized for the generation of zero knowledge proofs. On the Taiko documentation, you can see there is a very small amount of differences. That's why I'm saying it's almost type 1 ZK-EVM to how Taiko behaves from how the whole Ethereum ecosystem behaves. So there's some small differences to block gas limit, block gas target, and block time. So this affects some EIPs that are implemented in Ethereum. Just as an example, I have this very simple smart contract here written in Solidity. So it has a constructor, a read function, and a write function with some internal state. All we need to do is just change the RPC of which we're deploying the smart contract to, and we need to change nothing else. So the development process is exactly the same as it is with Ethereum, as we're going to see it is usually with pretty much every single one of the chains, with some exceptions, which we'll see later in the video. So just after compiling this smart contract using Hardhat, you can see here is the bytecode for the smart contract. Now this won't be as relevant for the next couple of chains, as the bytecode is going to be the exact same until we reach type 4 ZK-EVMs, where this bytecode is actually going to change. So once we reach type 4, I'll explain what the differences are in the development process and why we end up with a different bytecode. But for type 1 to type 3, this bytecode is going to be the same. So I'll just show this once here, and it's going to be the same for pretty much the next 3-4 chains up until type 4 that we look at. The first step here, as we'll repeat for each of the chains as well, is to bridge across from, in this case, the Sepolia Ethereum testnet to the Jolnir, I don't know how to say this, the Taiko L2, the ZK-EVM testnet that we're going to use to deploy our smart contracts into this Taiko testing environment. So what we need to do is send across our ETH over the bridge. Once we have the funds on the ZK-L2, we can go ahead and deploy our smart contract. Once that transaction goes through, you'll be able to see on the transaction section that you actually claimed the ETH that you bridged across onto the L2, which means we can go back to our contract deployment page, which we have here. So I'm just using ThirdWeb just to give you a simple UI to actually deploy. So you can see we're on the Taiko Jolnir, I think that's how you say it, L2, which is the Taiko testnet for this Taiko ZK-EVM. So I'm just going to set the constructor value here and go ahead and deploy that. The only thing that we've changed here is the network that our wallet is deployed to, which involves a different chain ID and a different RPC. Everything else is exact same as if I was deploying to Ethereum. The main difference here is this transaction is going to go through very quickly, and the fees are going to be very small. As you saw there, was around a 70-cent transaction fee to actually deploy the smart contract. So that transaction has just gone through in around 15 seconds, and the smart contract is successfully deployed. Just to showcase the kind of downside to type 1 zkEVMs is if I try and bridge back from the layer 2 back to Ethereum, this is typically going to take quite a decent amount of time. So if I send back 0.01, click bridge back to Ethereum layer 1, approve that transaction. This transaction is actually going to take a couple of hours for me to actually bridge back to Ethereum layer 1 because of the time it takes for a type 1 zkEVM to generate the zero knowledge proof and reach that transaction finality that is required for me to actually withdraw my funds back to Ethereum. The next one we're going to look at is Polygon ZK-EVM, which is currently a type 3 zkEVM working towards a type 2 zkEVM, which means there are currently some small differences in terms of opcodes, precompiled smart contracts, and other kind of minor differences that are required to be patched up to EVM equivalents in order to reach that type 2 status. You can see here on this page the actual specific differences that are required to reach type 2. So you can see here is the list of opcodes that currently are not EVM equivalent, the precompiled smart contracts, and other minor differences that Polygon ZK-EVM has kind of defined that are being worked on to reach type 2 EVM equivalence. This is expected to be completed pretty soon, so maybe even by the time you're watching this video in the future, type 2 will actually be the case for Polygon ZK-EVM. It's also a cool thing to note is that Polygon is actually working on both a type 2 prover and a type 1 prover, which is probably a topic for another video. But in the case of the public ZK-EVM chain, it is going to be type 2. So Polygon ZK-EVM has been in mainnet beta since March of 2023 this year. And the process to actually bridge funds is pretty simple. Again, you just go through this bridge UI. Let's say I want to bridge 0.005. Go ahead and agree to the terms and conditions and bridge your Ethereum across to the layer 2, which is the ZK-EVM. The mainnet environment here, you can go ahead and actually see the fees associated with this. So I'm bridging across around $10 worth of ETH. It's going to cost me $3 in gas fees. And I'll go ahead and confirm this on mainnet. You can see this is going to confirm my transaction here. And a couple of seconds later, the transaction was successful. We can go over here into this bridge section to see where we can actually claim these funds on the mainnet Polygon ZK-EVM layer 2. Again, like we mentioned earlier, the bytecode is going to be the exact same as you would if you were deploying to Ethereum. Only thing you need to change is the chain ID and the RPC that you're actually deploying your smart contracts to. So using ThirdWeb just for the UI again here to deploy our smart contract, you can see I'm just going to go ahead and fill out the constructor parameters, click deploy now. The process again is the exact same as it would be as if it was Ethereum. You can see the main benefit here is these very small gas fees, around 20 cents in a mainnet environment for Polygon ZK-EVM to actually go ahead and deploy the smart contract, which is a massive, massive reduction from what it would be on Ethereum. Go ahead and confirm this, and the speeds of the ZK-EVM will be much faster. You can see that was around 3 seconds for that transaction to be deployed and for that information to be fed back to my wallet. And as you can see here is the smart contract deployment. One of the big benefits to Polygon ZK-EVM and these kind of middle of the pack between type 1 and type 4 ZK-EVMs is that you get this familiar development environment where everything is exactly the same in terms of how you would build and deploy your smart contracts. And then the process for users to actually withdraw funds back to Ethereum via the bridge is much faster since it's more optimized for this zero knowledge proof generation. So as you can see here, I'm trying to bridge some funds back from the layer 2 back to the layer 1. If I go ahead and click bridge back to Ethereum here, go ahead and sign this transaction. Again, very small fees to perform this bridge. Approve that transaction. It will go through very quickly. That process is confirmed, and you can see here the claim will arrive in around 60 minutes. So this is currently around an hour. It's in the process of constantly being optimized and reduced to make this withdrawal process faster, but this is already much quicker than what you would experience on a type 1 ZK-EVM, since it is more optimized to actually post those ZK proofs back to Ethereum and reach that finality that allows for these withdrawals. One interesting thing about the Polygon zkEVM is that it actually is verifying this internal language made by the Polygon zkEVM team called Zero Knowledge Assembly Language, or ZK-ASM for short. The next chain we're going to talk about is Linea, which is the zkEVM built by the Consensus team. Linea is another Type 3 zkEVM working on the differences required to become a Type 2 zkEVM, which is fully EVM equivalent. Linea released their mainnet in July of 2023 this year and was released as a Type 3 zkEVM. As you can see in the kind of risk disclosure section of the documentation, it was a little bit buried, to be honest, but it is listed here that it says it does not currently approve 100% of the EVM opcodes and precompiles, which means, again, this is currently a Type 3 zkEVM. And in the roadmap here, if I can find it, you can see they're actually, again, specifically working towards reaching that 100% coverage to make them a Type 2 zkEVM, similar to what Polygon zkEVM is doing. The process to bridge to Linea is, again, pretty much identical to the experiences that we've had so far. You go through this bridge UI, enter the amount of Ethereum that you want to bridge over to the layer 2, commit that transaction by accepting it from your wallet, and this is going to initiate the bridging process from Ethereum layer 1 to the layer 2, which is in this case Linea. That bridging transaction has gone through. It took around 40 minutes for me to access the funds on layer 2. And now we can go ahead and do the exact same process. I've compiled my smart contract again using Hardhat for the exact same bytecode as we would with Ethereum. Gone over to ThirdWeb to show you the deployment process. Click the deploy now button. Exact same process for the Ethereum smart contract development deployment process for Linea. Confirm the transaction, and this transaction will go through. We'll have our smart contract deployed on layer 2 in just a couple of seconds here. So you can see that transaction was very fast as well, and we successfully deployed our smart contract onto Linea. The next one we're going to talk about is Scroll, and Scroll is another Type 3 zkEVM working towards being Type 2, which is currently in the testnet phase. In the Scroll documentation, you can again see the opcodes, the precompiled smart contracts, and the other various differences that are different from being exactly the same or EVM equivalent, making it again a Type 3 zkEVM working towards changing these small differences to become a Type 2 EVM equivalent zkEVM. Exactly the same as the other zkEVMs we've explored so far. The process is to bridge your Ethereum across to the layer 2, which is Scroll on Sepolia testnet in this case. So you bridge your test ETH on Ethereum Sepolia, which is a test network, over to Scroll Sepolia, which again is Scroll's layer 2 test network. So you go ahead and deposit your funds, approve the transaction, all of the same stuff that we've seen, and the exact same development process we've seen so far, where the same bytecode gets compiled. You're able to deploy the exact same bytecode you would from your Ethereum smart contract development process that you would to Scroll as well. So again, my funds took around an hour to bridge across on the Scroll testnet. Go ahead and deploy the exact same bytecode with this familiar process. Again, a very cheap transaction, around 50 cents to deploy this simple Greeter smart contract onto the test network. And this will hopefully take a couple of seconds for us to actually approve this smart contract, and then we can move on to the next one. That transaction's gone through, and we have successfully deployed our smart contract to Scroll. As we reach the final type of Type 4 zkEVMs is where it starts to get a little bit different. So a lot of the chains that we've seen so far, the development process has been pretty much identical to Ethereum, which is what we kind of love so much about the zkEVMs, is that you get access to all of the existing ecosystem of Ethereum, all of the dev tools, all of the wallets, all of the users are kind of easily able to onboard into these new chains and go back and forth between Ethereum and the layer 2 rollups. In the Type 4 category, we have zkSync Era, which is a Type 4 zkEVM, which has a very different approach from the other chains that we've seen so far. zkSync smart contracts actually compile into specialized bytecode, meaning the bytecode that you would deploy to Ethereum is different than the bytecode you'll deploy to the zkSync Era chain. Now, there's various pros and cons to this decision. So this enables zkSync to have kind of base layer changes to the actual chain that aren't possible on Ethereum. So things like native account abstraction are available on zkSync era where they're not available on Ethereum and requires this ERC4337 account abstraction with alt mempool, which I do have another video about here if you're interested in learning more. The downside to this is that you need to kind of keep these considerations in the back of your mind as a smart contract developer, as the differences between Ethereum and zkSync require you to have specialized kind of configuration in your smart contract development projects. And also zkSync has a full page of considerations that you should keep in mind when you're developing for zkSync coming from an Ethereum background. Here is actually the page that I'm talking about, the security and best practices page, which as you can see is very high up in the zkSync documentation. So this is something that they want you to be aware of. These are the differences that they have from Ethereum, which I guess you could say is the same as the stuff that we've looked at before, right? Each of the type 3 ZK-EVMs also had their own respective differences from Ethereum and from EVM that as a developer, you may want to be aware of. And zkSync also has this same kind of section where, hey, here is open and transparent differences that we have from EVM and from Ethereum that you might want to consider as a zkSync developer. So here are the code changes that I needed to make in order to get zkSync working. I needed to install this kind of specialized package from the Matter Labs team to plug this into my Hardhat configuration file. In this case, I'm using Hardhat as my smart contract development environment. And then I just needed to add this network section and a flag that says, hey, this specific network, I want to compile it for zkSync. The interesting thing that happens here is when you actually compile it, it's going to generate this new artifacts ZK and cache ZK folders that we didn't have before. So previously we just had an artifacts folder and a cache folder. In this case, we're actually generating specialized folders and specialized bytecode for the zkSync network. So if we dive into this greeter.json, you can see the bytecode is completely different to the bytecode that we saw utilized for all of the other ZK-EVMs that we've reviewed so far. So this is different from the bytecode which we were using for Scroll, Taiko, Linea, Polygon. All of the other ones that we reviewed so far have used the same bytecode that you would use for Ethereum, whereas zkSync is creating different bytecode. And this is kind of represented in this screenshot of the blog post I made about this. So you can see on the left-hand side, I think that's the left, is the typical bytecode that we used for Ethereum and all of the other ZK-EVM chains that we've reviewed so far. And then on the right-hand side is our new zkSync bytecode that we're going to deploy. So it's pretty simple to change, right? Only 3 or 4 lines of code to add support for zkSync compilation. And then when we go to deploy, we're just going to add this zkSync flag down the bottom here. And that is going to say, hey, actually read the zkSync bytecode, not the bytecode that we've been using previously. So this is just going to compile again. The zkSync ZK artifacts and ZK cache folders are going to get generated, and the exact same process is going to go through where we get the link that we can deploy using this UI here. I'll quickly show you again. I know you're probably sick of seeing it by now, but this exact same process where we go through the bridge, we send funds from ETH mainnet over to the L2 via a bridge. So we swap over to ETH mainnet here, continue. Again, this is going to take around 15 minutes in the case of zkSync. Send it over to the zkSync error mainnet. This is going to trigger this one transaction for us to actually say, hey, yep, that looks good. Send it over to zkSync, and that's going to take around 15 minutes. I actually already did it previously, so I already have funds over there. So I'll quickly show you again the exact same deployment process over on ThirdWeb. So we just type in the constructor parameters, select zkSync here, and we can go ahead and deploy this transaction to zkSync. I've just signed that transaction to approve the deployment, and in a couple seconds here, we should see the transaction go through. And here we are, 1 or 2 minutes later, the zkSync era smart contract has successfully been deployed. A special guest, as I mentioned at the start, is Kakarot ZK-EVM, which is coming out of the Kakarot ecosystem. So in the documentation here, you can see what is Kakarot. Kakarot is a groundbreaking ZK-EVM built on Cairo VM. So it's pretty interesting. Currently, they're aiming towards type 2.5 ZK-EVM, I believe. So Kakarot doesn't have a testnet right now. It's currently in development. But the reason I mention it is because Vitalik himself, among many other investors, have actually put some funds towards this Kakarot project to get it off the ground. So it's kind of interesting. I won't dive into it too much, and there's not too much we can show you right now because it's actually not even in a testnet phase, so we can't go ahead and deploy anything to it. It's just an interesting project coming from the kind of Kakarot ecosystem to give them some representation in this video as well. So to summarize this video, over in type 1, trying to match up Ethereum exactly, we have Taiko, which is currently working towards type 1 zkEVM and is in the testnet phase. In this bucket of type 3 zkEVMs, we have Polygon zkEVM, which has been in mainnet since March of 2023, and Linea of July 2023, working towards type 2. So they have a couple of different precompiles and opcodes that need to be matched up in order to reach that type 2 zkEVM status. And Scroll is in that same bucket, just currently in the testnet phase. In the pre-testnet phase, we have Kakarot, currently technically a type 3 zkEVM working towards type 2.5 coming out of the Kakarot ecosystem. Over in type 4, we have zkSync era, which has been in mainnet again since I believe March or April in 2023 this year. It is a type 4 zkEVM, which enables kind of unique use cases such as native account abstraction to the chain, but again, requires this kind of specialized knowledge and specialized setup in order to actually deploy that unique bytecode to the chain. So overall, it's not necessarily X chain is better than Y chain. There's different approaches that are being made to achieve this zkEVM. And it is awesome to see because the zkEVM was something that wasn't really expected to happen in, the next 2 or 3 years. And this is something that has been around for over 6 months now. And we're seeing more and more of these zkEVMs start to get closer and closer to a mainnet environment and start to see the adoption of these zkEVMs that are already in mainnet from the community today. So as you can imagine, I've spent a lot of time researching these different projects, where they're going, what each of them are currently up to, and experimenting and deploying these smart contracts onto each of them. So if you got any value out of this video, please don't forget to hit the like button. If you want to see more like this, subscribe to the channel. It is completely free. And if you do, I'll see you in the next one.